Okay, for this third video in section 2.2, we're going to look at a bunch of examples that uses our semi-formal definition of a limit in order to evaluate limits or argue that limits don't exist. So, just to start off, I'll note that what we did before in terms of the example we did at the very end of the previous video, showing that 3x plus 1 as x went to 4 had a limit of 13. You can do something very similar for constants and a constant functions. So we can say that there's a limit that says for any constants k and c, the limit as x goes to c of k is equal to k. That's not too hard to prove. That's something you could try for yourself. That's saying that, for example, the limit as x gets close to 4 of 7 is 7. 7 doesn't change. The limit as x gets close to 27 of 7 is 7. That's the kind of statement this is making here. Another thing says that, another part to this theorem says that the limit as x goes to c of x is c. As x gets, in some sense this is just saying as x gets close to 4, x gets close to 4. So, very, very simple things. It's worth knowing here. It's worth you taking a little bit of time to work these out, just like we did at the end of the previous video. But now let's do some more interesting examples. I'm just stealing examples from the book. I think it's a pretty good set of examples here. So let's take a look at f of x is equal to x minus 9 over square root x minus 3. So you might ask, take a moment to think about where this is interesting to ask that that we're doing a limit around, and it's going to be most interesting when the denominator equals 0, which is when square root x minus 3 is equal to 0, and so that's going to be when x is equal to 9 is going to be our key question. So we're going to investigate the limit as x goes to 9 of x minus 9 over square root x minus 3. So you can see once again, if you plug in 0, you're not allowed to, but if you could, separately in the numerator and denominator, you get 0 over 0. So this is an interesting question to ask. So 0 over 0 when x is equal to 9. So that's undefined. We want to try to come up with some value for it. So what we can do is that we can draw a picture. Again, this is something you can do with a computer, with a calculator, something like that. 3, 6, 9, 12. And so a computer, a calculator will draw something that looks like the following picture to you. There's just a little hint of a curve going on there. But really I shouldn't have drawn it solid, because we know really that there's a hole there when x is equal to 9, that this function is undefined. But we could take a dotted line over here to 6. We see that it sure looks like that as x gets close to 9, f of x gets close to 6. And so this is very good graphical evidence, and it turns out to be true, that this limit is equal to 6. In a future section, we'll be able to prove that this does equal 6. We'll be able to show that in section 2.5, but for now, pictorially, we see what's going on. We can also do this with a table if we wanted to do that. We can see that, for example, so let's make an x and f of x chart here. So when x is 8.9, then f of x is 5.983 ... When x is 8.99, f of x is going to be 5.9983 dot 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 8.999. F of x is 5.99983 dot dot dot, and we see that as x is getting closer and closer to 9 from the left, f of x is getting closer and closer to 6. Same thing, we want to reverse this and go, instead of going from the left, but go from the right. If x is 9.1, f of x is 6.0166 dot dot dot.